Hello, I'm Andrew Ferlitsch. I'm part of Google Cloud Developer Relations. So if you're not familiar with developer relations, we're that organization that's the outreach into developers, whether it's a developer community or into developers within our client companies. We're sort of the two-way interface between the developers and the Google product people. Today I'm going to be talking about transitioning into production. Okay. And so part of that sort of little intro is about infrastructure for production. And I want to start off with a little timeline why I'm bringing up transitioning into production. So in 2017, most of my interactions with people were about planning. They hadn't really started ML yet. You know, they were trying to figure out how does AI and ML going to fit into our business? What kind of skills do we need? How do we organize a data science team, you know? And then I found in 2018, most of the people I was interacting with were in what I called exploration. They were experimenting with models, building proof of concepts, MVPs, you know, and the business people were trying to figure out the value proposition, how's it going to fit in, and what is the projected ROI. Okay, and I think all those types of models are kind of like the models Hannes referred to earlier of the undeployed models. And I kind of think of it like back then every data scientist, their laptop was like the island of undeployed models, a really, really sad space. But today, I'm finding more and more and more of our clients and people in the developer communities, they're now ready to take those models and take them into a real production environment. And so we're in this sort of transition phase, and that's what I'm going to talk about. So part of being in production is having, like anything, the right things. So one of them is having the right framework, okay, and that's a production-ready AI ML framework. And that's what TF2.0 provides, okay? It's not to say, I always want to make this little note here, it's not to say that TF1.x didn't do production, is that TF2.0 was designed for production, okay? If you think about the more earlier versions of TF, when you look about 2016 and 17, people were doing planning. So it was meeting those people's needs. In 2018, people were doing development and prototyping. It was meeting those needs. Now that we're in production, again, you see a revamp in TF2.0. But I'm not going to talk about the new features and all that in TF2.0 because that's already well covered by the TensorFlow team. Another important item is, of course, your pipelines. Those are having those production-ready pipelines for training, versioning, and serving your models, and that's what TFX is. Okay, and if you're not familiar with the history of TFX, is that it's actually what Google used internally across all its own business organizations to serve its own models for 6 years before it was even open source. So it was already a very well-developed production system for pipelines. And then finally what we're finding is you need a platform. And your platform are your managed services. This is particularly important to the DevOps people, but also the product owners. And that's things that it's going to handle is like your retraining, your versioning, the deployment of the models, the distribution, and everything. And here at Google, you know, our AI platform is the GCP AI platform. So just a quick little plug there. If you haven't looked at it, please do. Okay. So this kind of depicts what today a modern production flow is going to look like. So you're going to have at your company some kind of data repository. This is where all your data is. And you're going to have data engineers that are going to come up with methods, identify what data is relevant, what data you're going to use, and it's going to come up with data distribution strategies. That is to get the data from the repository feeding to the model training thing, the right data at the right time, okay? Then we have model training. You know, we've long gone past the old days of being on a laptop and serially training one model at a time. You're either using large hardware or you're on cloud and you're training multiple models in parallel. You might even be training multiple instances of the same model in parallel, okay? The next step is as we train the models, we go through this validation step. We're going to make a decision whether this new version of the model is better than the old version. If it's not, we obviously go back, continue the train. And we're going to have some kind of train model repo that when we decide something's better and we version it, we got a way to store it. Now it's just like source code. It's a version 1 of the source code, version 2 of the source code, now it's of the model. And that's going to have metadata that we're going to use to make evaluations about whether this is a better version. Assuming it's a better version, we're going to deploy that model. And when it's deployed, we're still not even done. Because what we think in-house that a model is better than the other one, we really don't know until it's actually out in the wild being used by people. So there's always some version of sort of checking, we usually call it A/B testing. Some number of people are going to get the previous version, some number of people are going to get the new version, and we have some kind of metric that company will have to measure which one is performing better. And that's our A/B testing. And from that, insights will be collected. And those insights will lead to additional data being collected and labeled and added to the data repo. And this cycle just continuously goes. Okay, so I'm going to talk about a few things that are a lot to do with TF2.0. They're more recommendations, not necessarily features, about what's good for production. Okay, and one of the ones I really like is the idea of moving data preprocessing into the graph. Okay, so I'm going to be highlighting things like a TFT transform, the TF function decorator, and subclassing. Okay, so prior to this recommendation, TF2.0, generally we did our data preprocessing upstream from the model. So if you're not familiar with data preprocessing, would be like your feature engineering, your normalization for an image, things like that. It's really to say is how do I take my data from its native format and get it into a machine learning ready format that can be fed into the model during training. The problem is when you did it upstream, that happened on the CPU. And the training happens on the GPU, and you have to be able to process your data fast enough on the CPU that you're not being the bottleneck and starving the GPUs. Okay, and of course we've had a lot of great things. With TensorFlow TF.data, we built in prefetch, assuming you had a multi-core CPU, so that you're actually using multiple cores, getting the next batch preprocessed. But still, as you scaled up on a single instance and added more GPUs, sooner or later you would end up starving your GPUs. Okay, so what they came up with was the idea is this come up with additional graph operations that support transformations of your data. Okay, and then those can be added to your model, and we can move. So like I said here, oops, there we go. Okay, we can, the old way where we did it on the CPU, we basically now make what I call the data distribution. That input function that you all remember writing, that separate input function, you write the model, then the input function. Well, we don't write the input function anymore as part of the data distribution. That's why I show the icon smaller. Instead, that's now part of the model. And so it's going to run on the GPU. So if we look at even a bigger picture here, is in the old practice, what we did is when we had that separate input function, we had to also re-implement it on the deployment side. That is, when you fed something for a prediction, it had to be pre-processed in exactly the same way it was for training. So we had this duplication. Okay? If you look under the new version, by building this now right into the model, it's already there in the model when we deploy it. We don't have to re-implement it on our production pipeline. So all that pre-processing is transformed to graph operations, and there's a program that's built into TensorFlow 2.0. It's called Autograph. It's a compiler. okay? It does several things. It knows how to optimize graph operations to make your graph run as fast as possible, but it also knows a lot of other things that can be converted into graph operations, which we're going to go into in a little bit. But by doing so, our data preprocessing is now happening on the GPUs, so they're not being I/O bottleneck waiting for upstream preprocessing. We don't have to re-implement it on the side. And another thing I really like about this is the way they've implemented the TF Keras and the subclassing is we can now do what's called pre-stems. That is, we can now add layers in front of existing models without rebuilding and retraining them. And we can actually implement this through a pre-stem. So, conceptually, today's modern architecture, and I'm just going to use a convolutional neural network architecture, looks effectively like this. Okay, I would say ever since like about 2015, with a residual network, it's kind of followed this general architecture, where we have a stem convolution group. That's what takes the initial images coming in and builds the first feature maps. And then there's a sequence of convolutional groups, okay? And then finally a classifier, and that's sort of our macro architecture, okay? And then inside of these, how they're implemented, that's what we call the micro architecture, okay? What we're finding today in modern stems is that some of them now have a pre-stem. And that's what we're going to talk about. So let's start off with what subclassing is. So Keras, or TF Keras, is built on OOP, object-oriented programming. So it supports everything from polymorphism, abstraction, inheritance. So we can actually use inheritance. So the underlying structure for layers is the object layer in Keras. So we're just going to subclass it and make a new one. And the important three built-in functions that we have to redefine are these: init, build, and call. Init is just your instantiation one. Build is what happens when you go .compile and it assembles your model. For every layer, it's going to call the build method. And when you're actually executing your model and you're feeding data through it, it's the call method that's called. Okay, kind of already covered that. So, let's see, I'm going to build one. I'm going to create a new layer. I'm going to call it normalize. And the whole job of this one is, I'm assuming this is for image preprocessing. So we know our image data is coming in really as pixel data. Those are 8-bit integers between 0 and 255. I want to convert it to a floating point number, and I want to divide by 255 so every value is between 0 and 1. Real simple. Okay, so I can easily build a layer here. Okay, I'm going to call it normalize. I'm going to inherit from .layer. A few things I know. This is a straightforward algorithm. There's no learnable parameters. Therefore, I have no kernel. That's why I set kernel equal to none. That tells the compiler process to not do backward propagation and try to update the values in here, because there are no trainable ones. And then in my call function here is where I'm going to implement, this is the input tensor coming in, and I'm going to just divide every element in that input tensor by 255, and then I'm going to add this decorator. And this decorator tells autograph to change this into graph operations so they get added to the graph. So none of this will occur on the CPU. Okay, so I've kind of already covered that. So let's look how I might implement that. So think of this as removing this line as a very simple minced model you might use. I'm going to use the functional API here. So first I declare my inputs, right? And then my first layer, I'm going to have to flatten them. So after flattening, I'm going to have one or more hidden layers, dense layers, and finally my output dense layer for classifying the 10 digits and then pulling it together. Well, in between, I just added this new layer. So I'm going from input to normalize, then flatten. So now I could just feed this model the original minced images and just take them straight as is. I don't have to do any pre-processing. You can do this, as I mentioned, with a pre-stem. Okay, here's the simplest way to add a pre-stem. Think of it this way: if the output of your pre-stem matches exactly your input, you can use the sequential API to just attach them together. So I have some existing model. Let's assume it's that minced model. Okay. I'm going to make what I call a wrapper model. I'm going to make a wrapper around my existing model. It's going to be trained or untrained. Okay. And as the first layer, I'm going to put in the normalized one, and then I'm just going to add my existing model. So I've just attached the pre-stem to the stem entry point of my existing model. Now I got a wrapper model. Go ahead and compile it, and we can use it as is. Okay. So that's kind of like moving data pre-processing, but once you're moving data pre-processing, really one of the goals in TF2.0 is to get people to start thinking about what else can I move in the graph? How can I make my graph even more of the application? So, the one I like to do is start thinking about data augmentation when you're training. Why not build the data augmentation right into the graph instead of making it an upstream process? Okay. One of the benefits if I can get in the graph is now I have consistency in the data augmentation when I'm retraining. I know for certain when I retrain that model, it's going to be retrained with the exact same data augmentation I had before. If I'm going to reuse some pipeline, it eliminates my need to re-implement the data augmentation on that new pipeline, because in effect, the data augmentation is now built in the graph. So if I'm doing transfer learning, the data augmentation comes with it. And by implementing it as a pre-stem, which I'll show you in a moment how to do it, I kind of now have a plug-and-play augmentation pipelines. I can build these data augmentation little mini graphs and start putting them on different models, reusing them. Okay. So in this case, I'm going to subclass a new one called mirror. So that's just saying is when I get an image, I want to make a mirror image of it. So that's just a vertical flip. Of course, I don't want to do it on every one. I'm not going to go into the code in too detail, but I use a simple toggle here. Every other input, so you see that flag, and then I toggle it. So every other batch it sees it will flip. So the first batch won't be flipped, the next batch flipped, the next one not flipped, and so forth. Okay. The key thing is I only want this layer to happen during training, right? It's in my model. When I deploy it, I don't want it doing data augmentation. So there's a back-end function in here called in training phase, okay? And that function only executes when you're in training. So I put all my code in this little embedded function, passed it here. So what will happen is that during training, this code gets executed, the data augmentation will occur, okay? But in evaluation or prediction phase, this becomes disabled and this layer just is effectively not there. It's actually the same way that dropout is implemented. You know, if you put dropout in your model, it occurs during training, but it somehow magically goes away. If you read the source code, you'll see this exact same line in the source code for dropout.
Like with image generator, like when you implement it, it does the same thing like during inference, it doesn't apply.
Right.
Right?
Yeah.
So what's the advantage then over not using like image generator?
Well, I think you have to, you know, if you look at the sort of how they merged Keras into TensorFlow, they merged the model API. So one can kind of think, well, the Keras data management, data feeding system is still around. Really, the emphasis is to go with the TensorFlow ecosystem around the Keras API. Okay, so here's just an example now where I've just gone a step further. So making my model, I have my inputs. This is like for a CFAR10. Normalize it so I don't have to pre-process it. Put my data image augmentation step here. Rest of the model, finish the model, go train it. While training, this layer is executing. When I'm in evaluation, it becomes just a direct pass-through. Okay. Warm-ups, here's another thing. Okay. Another thing that we're really encouraging is the idea of doing a little bit of pre-training on your model before you go into full training. Okay, we already think of it when we're training. You know, we used to go do, in the early days, one set of hyperparameters and you just do a full training and see what you got. If you didn't like it, you did another set of hyperparameters and you did a full set of training. Then we kind of evolved around with the idea of hyperparameter search, where I take some set of parameters and I train for a while, but not completely, right? And I look what I got, and then I keep doing that more efficiently until I find that best set of hyperparameters, and then I do my full training. The problem with that approach is it overlooks the importance of the initial weights, okay? So we kind of all know, have a lot of experience in knowing how important getting the right learning rate and learning rate schedule is for training. But what we have found, and there's a great paper on it called the lottery ticket hypothesis, okay, is that that draw, when your model is initialized, it's taking a draw from some random distribution, and every draw is different. And some draws are better than other draws, okay? And they can make the difference about how fast your model will converge and whether it will converge on the best or global optima, okay? And in the lottery ticket paper, what they showed is they took why very large models work, okay? And when they studied them, they found that they were really a composition of lots of little models. It was like models and models, where every one of them was a separate draw. Having an initialization, it was like having a separate draw from that random distribution. And so it was like each one had a lottery ticket, and one of them was the lottery ticket. And the way they were doing the paper was trying to figure out how to cut out that little model, pull it out, and say, that's the winner. Okay, but we've taken that concept now into warm-ups, and generally the recommendation is let's take, before we start our hyperparameter search, okay, let's take like several copies of the model, each of them having a different initialization, start with a really low learning rate, okay, and just very short runs on each one, and look really closely at the stability of how it's increasing in accuracy and the valuation loss is going down, and use that to say, that's the best initialization algorithm, that's my winning lottery ticket, I'm going to start with that instead of a random one before I go into my hyperparameter search. So that's kind of how things are changing. That was the general practice, and now the general practice is to not start with just some arbitrary initialization, but to use the warm-up phase to find the best initialization, use that model, and then move into your next step. So here's like if you want to do it by hand, how I would do it. So I've created some model here. It's not compiled, and I'm going to save it. Okay? And remember, I don't care what default weights are in this model, because I'm not going to use them. Okay? So this is one of my little favorite tricks here. So I got a really low learning rate, and I'm going to get 5 copies, and I'm just going to keep reloading a copy. Okay? Here's the thing. I want to give each one of these a unique set of weights. Okay? And so I can go from the model .get weights, get its original weight sets, and I could also feed it right back and reset all those weights, right? But I want to change them, so I know this model used a E-normal distribution, so I'm just going to get some kind of random draw from that E-normal distribution that's different than a previous draw, and reset it. Here's the key thing. Sometimes I see people doing this in blogs or Stack Overflow, and you miss this line right here. These weights are a combination of really the weights and the biases. So the weights are always going to be numbers between 0 and 1. The biases are always going to be 0 or 1. And if you start replacing those zeros and ones with those little numbers like 0.32, 0.85, it's not gonna work. Your model's gonna take longer to learn, it may not even to convert. The nice trick is in these models, what I find is the biases are always 1D vectors, and everything else is 2 or 3D. So I just have this little embedded if statement that only if it's greater than 1 dimension, then I know for certain it's weights do I replace the weight. Otherwise, I retain the 0 and 1. So that's how I can get a unique distribution each time when I'm reloading the model from my disk. I compile it. I do my short warm-up test, so just a short number of epochs, a short number of steps per there. I keep the history, I'm going to save this history, and based on the history, I'm going to make, somebody's telling me I got 5 minutes. Deconvolution. Okay. Here's another one. So a lot of people are used to convolution. Deconvolution is really the reverse, transpose, but you can use it in a pre-stem to solve problems. In a convolution, when it's strided, that means your strides are greater than 1. You're actually making your input feature map smaller. In deconvolution, you're doing the reverse. Deconvolution is the same. Instead of using a static algorithm to upsamples, you're learning the best algorithm for your data, and your model upsample your data. Okay, so I can use this if I have an existing model that's trained for 1 input size, let's say 120 by 3, and it's already trained and I want to reuse it, but I got a new input size that's a lot smaller. Okay, what would I do? Well, I can again use a pre-stem, and I can use deconvolution to sort of scale up the 32 by 3 to that size, but not do it statically, but actually learn the best algorithm for doing it for that data and that model. It's real simple. So let's say I got a ResNet 50 here, okay, and I configured it to output, this is for CFAR 10, for the 10 classes. Okay, as you can see, I got a version that's 128 by 3. Okay, that's just to show, hey, that's really what it is. Okay, so now if I want to add that, again, I'm going to make a wrapper, sequential model. I do 2 deconvolutions. By setting my stride to 2, I'm going to double the size, so it's going to go 64, 64. I'm keeping the same number of channels. I want the thing to match. I repeat it again. Now I'm at 128, 123. That now matches the input of that ResNet. I can bind them right together. And now when I train, it will learn the best way to upsample those images so that this ResNet 50 can learn. What's interesting about it is these concepts weren't around in 2015 and 16 when the ResNet V1 and V2 papers were published. And when they tried to use the original ResNet architectures, they couldn't train it on CFAR 10. They couldn't get it to converge. They had to actually make a reduced version of it, a specialized version, which they called ResNet CFAR 10. Okay, and on that one, they were reported getting about 92, 93% accuracy back then on 200 epochs. But remember, they couldn't do it with a ResNet 50. I took a ResNet 50, I used my deconvolutional pre-stem, I had no problem with training, and I got the same accuracy in 50 epochs. So using deconvolution in a pre-stem, I could accomplish what they couldn't accomplish back then, and I got something that was as accurate, trained faster, and no redesign of architecture. And this is probably a good point to quit so some people have time to ask questions.